Hi everyone, this is a small tutorial on oscillators which I'm going to show you how to do a simulation in Cadence. So let's start with our library manager. So I have my Cadence tutorial library already created and I'm going to make a new test bench. So file, new, cell view, and here I'm going to name this as tutorial ring oscillator, and the view is schematic, and we'll open with schematic L, and it brings up the schematic L window. So I'm going to start by building a ring oscillator here, which is 3 inverters or odd number of inverters, to just show you how to do a basic simulation. So let's go to create instance I or bind key I. So I would say browse. This time I am not gonna use the PDK90 library. Instead I'm gonna use another library called GSLB090. So this library has all the logic gates that's already implemented and stored in Cadence. So since I have my show categories, it's showing me the category view of all this. So I'm going to use the inverter, and now you can see there are multiple inverters in as cells. So the difference is each inverter is different from its drive strength capabilities. So I'm going to use the minimum right now. So there are two things. So you have the symbol and the symbol IPT. I'm going to show you both. So if you highlight on symbol, you get the typical symbol of the inverter, right? So if I use the symbol IPT, it's again the same thing, but you could see there are two different pins, which is extra, which is the power supply pins to the inverter. So this is not there in this symbol. So I'm going to use the symbol IPT to do this. So I'm going to delete that. So let's zoom in. I'm using the parenthesis keys as usual. I'm going to copy this inverter, make them stage. I'm going to wire them up using the wire command. So I'm going to feed back the signal here, and let's connect the that didn't look good. And if I want to undo, so I could use the bind key U, or I could go to edit undo. So that went. So I'm going to add the wire again here, and so what's left is just the supply connection. So instance I, gonna choose the analog library, go to sources, independent. I choose the VDC. Here's the symbol for it. And I will choose my supply voltage is 1.2 volts. There, escape. Wire that to my power supply, and I need the grounds, so I'm gonna go create instance. Since I already know what component it is, I could just type GND. This is just a quick way of showing you that once you get used to Cadence, you kind of remember the cell, and you could directly get that instead of doing the browse. So you can abut that. I'm gonna do that too, and I'm going to connect the ground there. Skip. So this looks good. Let's try to simulate. Before that, we gotta set the output. So let's have a output pin here for the oscillator. So P pin. I'll change the direction to output. and pin name can be oscillator underscore out, and here's the pin. Escape key F, just to show you that the oscillator is complete. Now I'm going to start the ADE tool to run the simulation. So I'm going to launch ADEL. So that brought up my analog design environment tutorial for Cadence. And I'm going to say, I'm going to first check whether my model libraries are okay. So if they're okay, they are set to whatever is defaulted, and I'm going to run a typical simulation. So I'm just going to, oops, sorry, there you go. So I'm going to see if there are any design variables here. So variables, copy from Sylview. No, I don't have any design variables. It's pretty good to go. And now let's run a choose analysis. So I choose this icon for analysis. So there you go. I'm going to run a transient analysis. Say let's run this for 100 nanoseconds. And here in Cadence, the Spectre simulator asks for how accurate your simulation is. So if you choose liberal, your results may be off by little. If you use moderate, it's within this range, and if you use conservative, it's really the Spectre simulator takes care of more accuracy. So I just choose moderate, and then make sure you're enabled simulation, and just okay. That came. Before that, we forgot to check and save the design, so let's check and save the design. Okay, everything looks good, no errors. Let's check that. So it said schematic check completed with no errors, so that's pretty good. Let's go back and then set up our outputs. So I'm going to say outputs to be plotted, select on schematic, and I'm going to give the output oscillator. So this got highlighted here. And here's what, so you could even save the plot if you want to access this in future. So you can check that too if you want. So let's netlist and run. So it started running. Wow, there's nothing. So the reason there's nothing is in an oscillator, it's the oscillations start by the noise that's induced in the circuit. But in our case, the simulator has no noise. It's not taking any initial conditions to do it. So you could approach this problem in two ways. You could set initial conditions by going to simulation, convergence aids, and you could set initial conditions. So you could select the node voltage which you need to go, so you just click on that, and it assumed to be a ground. So initially this is going to be a ground, and it's going to start. So let's see if this works. Or just another way of doing it is I would cancel that, I would break the loop here, and I will add a piecewise linear source which kind of starts up in the simulation. So I'd say instance I'll go to the analog library and say browse, go to sources. This time I'm gonna go to an independent source again, and I would use a VPWL, which is called voltage piecewise linear source. So I'm gonna click symbol here, and this I'm gonna give, say, 3 points, or you could even have a 5-point resolution. So you could say at time 0 nanoseconds my voltage is 0, at 1 nanoseconds it could be 1.2, or I'll choose 4 maybe, yeah, 1.2 volts, sorry. At 1.1 nanoseconds I would still keep it at 1.2 volts, and at 1.2 nanoseconds I will have it to 0. So basically this during startup the simulator is going to take this condition, so I'm gonna just hide it and I'm gonna insert this in the feedback loop. So escape, like that, check and save. It's okay, and you could even run the once you've set up, you could just run the simulation here. So just saying run. So it's kind of running my simulations. Now it seems to oscillate. So basically I added the source so that the simulator understands that the oscillator's initial condition is met. So I'm getting the oscillation output. So I could do one thing. I could use this little tool to zoom in to see how my oscillations are, or I could hold down right click and drag in the mouse. That also gives you a fine way of estimating or zooming in to a particular so you could see the oscillations got clamped to the supply voltage, almost to supply voltage, and you're getting the oscillations. Now if you want to find the frequency, I can show you another way where most of them use this. You use the calculator. Cadence has an inbuilt calculator which can calculate different parameters for you. So I would just click on the waveform here and send it to or rather I would just take this thing and then send it to the calculator. So it took the results of the transient simulation here, and I would just say there's a special function tool here which you could find a lot of functions. So I'm gonna find what is called frequency. So it's right there. Just gonna click that. It's asking what's the signal to be plotted, which is the output, what type you want, rising edge, falling edge, and the threshold. If you want to just say, you can leave this to defaults and say okay. So your formula got changed, right? So let's add. You need to plot this. So what I would do is go to outputs, setup. In setup you get another window here. You could say new expression. So what happens is you could give a name. So I want this is the frequency, and in Cadence if you want the formula that is present in the buffer here gets copied here if you say get expression. So if I click on get expression, I'm going to get that formula. So if I do that, I got that, and you don't forget to add this here. So just say add. Okay, if you see here, it got added here. So there's another way. If you don't have to since this is just a calculation done by Cadence, you don't have to netlist and run the whole design. You already have the result, so you can just say plot outputs here. So you just click that, you'd get a wave here. So it's kind of oscillating at 16 gigahertz, which is a little unrealistic, but it's fine. It's just a tutorial to show you how you could calculate the frequency. So it's just getting this value here. So this is the basic simulation here. So I would rather want to do other analysis like steady state to determine the phase noise of this oscillator. So I would go to analysis. This time I will choose PSS, which is the periodic steady state. So I have a nice window here, so I leave this to shooting. So I'll just say my peak frequency is around 5 gigahertz. I want 10 harmonics. I would do a moderate level, and I'd say it needs some time for stabilization. So you could do one thing, you could see where your oscillations are getting stable. So I would say, just by the rule of thumb, maybe after let's go a little forward. Say maybe let's start it at say 40 nanoseconds. So I could just give that. So it's pretty stable after that. So I'm just going to give 40 nanoseconds. and you could say save initial transient results. And since you're doing an oscillator design, you could click this oscillator and it's going to ask for the nodes for which it's going to, so I'm going to select the output node and the reference node. So just say select that would have got reflected here, and the reference node is my ground node here. So came, and make sure you enable and just say okay. So that came to PSS. Now in order to get the phase noise, you have to run the phase noise simulation. So I'm just gonna go to analysis. This time I'm gonna do P noise here, and I'm gonna give a start range, say 10 to say 20 gigahertz maybe, and you could say at specific point because you want to see at 1 megahertz, for example, maybe here, and you could say maximum sideband I need to be 10. You could choose different values based on them. I'm just showing you some examples. So output port, it's asking for output. So I just say instead of probe voltage, it just pops up saying it needs this thing. So I'm just going to have the positive output node and the negative output node. So again, I choose the positive output node here, and the negative output node here, which is the ground. So I got that, and oscillator doesn't need an input, so I'm just gonna make it none. So just say enable, apply, okay, and you have it here. So I would have to put a formula to find phase noise. So let's do this again. Outputs, setup, say new expression. Type this as phase noise. I just say open. That opens our calculator. You could clear the buffer just hitting the escape or the delete key. So you could find a function here called phase noise. So you can use that. And here it asks which harmonic. So I want the first harmonic here. So you're only interested in the first harmonic phase noise, and signal data preset has to be from the PSS. So I'm just not using harmonic balance, I'm using a PSS analysis to do it. So it takes the value there, and the data is P noise. P noise. You could just pull this out if you want and see what it is, and that's about it. So this gave this. And what you have to do here is, again, you have to find the phase noise at 1 megahertz for 1 megahertz, for example. So what you could do is choose value. There's a function here called value. So if you click that, it asks interpolate at. So I would say 1 megahertz and say okay. That's going to change your expression here. So it's a wrapper function around your phase noise, and you can just say get expression. So you got that. You could say add. Okay, close these, and I'll save the state. So I just say click save state, go to directory, say okay, saved, and now you could run the simulation. So netlist and run. So this is going to run a transient simulation followed by a periodic steady state and the P noise. So that added this, and it kind of calculated your phase noise, which is really poor in performance, but it's just a tutorial to find out how to do the phase noise. So typically this has to be much better, but since it's a ring oscillator, the noise performance is poor. So this is how you run simulations for an oscillator, basics, and here's your window regarding your frequency your waveform. So thank you for watching.